All right. So folks, we took a look at this 9.1. I kind of threw you into this question about going to the zoo and how much it might cost, and ultimately to figure out how many children and how many adults visited the zoo. And so there were 4 parts that I wanted you to go over in your small groups. I'm wondering if folks were, if there was any particular place where folks were feeling stuck. That way we can sort of target what we do as we're going through this. So how did we feel about part A?
At first, for at least me, it was kind of tough to set it up into a system of equations, but I forgot who it was. I think it was maybe Ian. Basically broke down the second part, that on a given day, 2,000 children and adults. It was just, kind of reading the question properly and trying to figure out, okay, how do we set this up to make a systems of equation from a word problem.
Yeah, I think that is probably the hardest part, which is why I wanted to just make sure that it was like right there in front of us. Because I think sometimes we're like, well, I know I can solve it once I have the equations, but we're reaching a point in our academic careers where it is really beneficial to also cultivate the side of us that can translate a word problem into equations. And so do any of the groups, or well, there's only 2 groups, but did either group end up with a system of equations?
I think both of us did, but I know my group did.
Yeah, what'd you get?
It's a funny thing. Originally, we used the variables A and C for adults and children instead of X and Y. So our graph was interesting. But we got, for the first equation, 70,000 equals 25X plus 50Y. And for the second equation, we got 2,000 equals X plus Y.
All right. So hopefully you ended up with something like this. And one thing that I kind of want to point out is that usually when you're looking at these kinds of questions, if you're asked to sort of group them into or write them into an equation, what you'll usually end up with is one equation that is about money. All right, so if your word problem involves something about cost, there's usually one of the equations that's going to be centered around the money. Okay. The other equation is usually counting some kind of thing. Okay, and in this case, we're looking at people, like how many people, children and adults, attended the zoo on that given day. Okay, and so if you are, feeling stuck on how to kind of start these writing of the equations, you can think about it in this framework of money and things. Like there's probably a money equation, there's probably a things equation. And if you can sort of separate those, then it might help you write those equations a little bit better. Okay. Now in part B, I asked you to use Desmos to graph things, because one of the beautiful things about Desmos is you can put the equations in just like this. You don't have to rewrite it. You don't have to solve for y, find the slope, find the y-intercept. If you plug these equations into Desmos, it will give you a graph. You just have to zoom out enough so that you can kind of see what's going on. But effectively, you should have ended up with one graph that kind of looks like this. Okay. In particular, that would be the number of people that are going to the zoo in terms of like children and adults. And then there should be a second line that kind of looks like this. And this one would correspond to the money, the cost of, or, whatever people paid to go to the zoo. So the question said, use Desmos to sketch or to graph the system of equations and find the solution. Where is the solution on this graph?
The XY intercept. No, like where the lines intercept each other.
Yeah, exactly. That intersection point. And the other nice thing about Desmos is if you click right on that point, it will give you the coordinates. And so if you had clicked on that point, should have given you this value, 1200 and 800. Okay. Let's be a little bit more thorough. What would we label this horizontal axis? Like what is that horizontal axis measuring? Yeah, on this axis, we've said that children we're going to call X, right? So maybe over here, we could say X equals the number of children. That would make Y equal to the number of adults. Right, so number of children. This would be number of adults. And so technology is definitely really useful because like a lot of the problems we've done so far, sometimes I'll be like, this is the answer. Now we have to figure out how to get the answer in a different way, right? So we found our answer. We know that if there were, the gate revenue was $70,000, that there were 1,200 children who went to the zoo that day and 800 adults, okay? So then in part C and part D, I asked you to solve the system of equations using substitution and then using elimination. Two different methods that you learn at some point in your academic career. And the substitution method will get you the same answer as the elimination method. And I think sometimes when we're learning these methods, teachers are like, pick one that you like and don't worry about the other one. You don't have to know both, okay? But I think that part of what I'd like us to view these multiple strategies as is that sometimes using substitution is going to be more straightforward, make the problem shorter. We have to use less ink. And sometimes elimination will serve us better, okay? And so knowing how to use both methods is important because as we're going to see later in class today, sometimes we have to use both methods to solve a more complicated problem, all right? So let's start with the substitution. What would we need to do to this system of equations in order to make it into something where we could use substitution? Were you folks able to get that far in your conversation?
Yeah, so our group, we, for the C plus A or X plus Y, we subtracted one of them. We chose the A. So it was 2,000 minus A, and then we just plugged that into the revenue equation.
Okay. So you did 2,000 minus A. So if we grab this equation and we say, okay, we have 2,000 equals X plus Y, you said X equals 2,000 minus Y, yeah?
Yes.
Okay. So when we're doing substitution, okay, we need to think about like our choices here. I would absolutely agree. We should pick this yellow equation to get one of the letters by itself, because we can do that just by either subtracting the X to the other side or subtracting the Y to the other side, right? We don't have to divide anything. So it's a little bit less work on our end. But now we have this thing, right? We have that everywhere we see an X, another way of writing it is 2000 minus y. And so we can take that and we can put that into that red equation right there. So we have 70,000 equals 25, but everywhere I see an x, I'm going to put 2000 minus y. And just as a reminder, this is the same thing as the x that was there. Now, what's the benefit of doing this? Like at this point, we should be like, yay, I'm in a good place to solve this problem. But why?
Because we can solve for just y. We've eliminated at least one variable.
Exactly. We have one equation and one thing that we don't know, right? And so let's work this out. I think we get 50,000 minus 25y plus 50y. And so I'm going to subtract the 50,000 to the other side. I get 20,000 equals 25y. And I end up with y equals 800. And we said earlier that y is the number of adults. And when we graphed it, we found 800. So that is awesome, right? So far, our answers are checking out. But if you stop here and you're like, I'm all done with the problem, ready to turn in my test, I would be like, ooh, sorry, I can't give you full credit. Why can I not give you full credit on just part C?
Because you haven't found x yet.
Yeah, we didn't find the other letter, right? And I think sometimes we're so caught up in the process that we forget about these super common mistakes, right? So all we need to do to finish the problem and earn full credit is to make sure we find the other variable. And here's the nice thing about substitution. When we use substitution, at some point, we find an equation where it's going to be really, really straightforward to find the other variable. And so in particular, if I have x equals 2000 minus y, everywhere I see a y, I can put in 800 and I'll get x equals 1200, which matches the number of children we saw on the graph. We'll do a couple more examples of substitution later today, but I just wanted to kind of give us an overview of how that works. Again, some of us, we might be super strong in this. Others of us, it's been a while or it didn't ever really quite make sense. And so I want to just make sure that we can sort of establish some kind of common ground here, okay? All right, now, truth be told, if I were solving this equation, I would definitely use substitution. I probably wouldn't do elimination. But I'm wondering if I wanted to use elimination here, what needs to happen? Because as the system of equations stands, we cannot use elimination right off the bat.
So our group, we chose to multiply the things equation by 25. So everything by 25.
Cool. So you took 2000 equals x plus y, and then you times by 25. Why'd you pick 25?
Just because whenever we would subtract the y's, it'll give us a number that we can then divide.
Yeah. These 25s, it's going to make these x's have the same coefficient, okay? So if we multiply this by 25, then we'll get 50,000 equals 25x plus 25y, all right? And elimination is the method where like you kind of stack the equations on top of each other, right? And so this is sort of like the new yellow equation. And now I'm just going to write this red equation and yellow equation like literally right on top of each other. And so I'll get 70,000 equals 25x plus 50y. And then the yellow one, which is 50,000 equals 25x plus 25y. Now, keep in mind that our goal here is to eliminate or get rid of one of the variables. And so in order to do that, we could subtract this whole equation. All right. But you'll notice that I'm putting parentheses around the entire second equation. So we want to make sure we subtract every single term, right? So if we subtract the left-hand side, we get 20,000. When we subtract 25x and 25x, we get 0. But what do we get when we combine these last terms?
25y.
Good. I've had more than one student write that as 75y. Why would they think it would be 75y?
Because they didn't look at the subtraction symbol and they just looked at the addition.
Exactly, right? So this negative is distributed to everything in here, and you got to make sure you're actually subtracting, okay? But here we can see we end up the same thing that we had over here. We're going to end up with y equals 800. How do I go back and find the x value if I'm using elimination?
Could you just substitute it back?
Yeah, into where? Where would you like to substitute that in?
2000 equals x plus y.
Yeah, we can go ahead and put it right into here, right? We can say 2000 equals x plus 800, and then we can subtract 800 and we get x equals 1200. Okay. So hopefully a good refresher in terms of all these different pieces of our algebra skills. These are definitely ones that we use in a lot of different contexts, as we'll see this week, okay? All right, so like I said, we're gonna spend some time doing some substitution, doing some elimination today, but I wanted to at least give us a chance to see an overview of like where we're going with this problem, all right? And hopefully recall some of those memories somewhere in our brains, all right? Okay. So let's take a look at these types of linear systems, right? What lesson would we have if we didn't introduce some vocabulary and make sure that we could not only do the mathematical work, but that we could also speak and write and read like mathematicians, okay? So it turns out when we're looking at types of linear systems, there's actually 3 types, all right? There's one called consistent. And if there's a consistent one, it would make sense that there's also an inconsistent one. And then in the middle, there's a special one called linearly dependent. All right. And so, yes, these are words, but I think that for me, it's always easier to remember the words if I sort of have a picture to sort of ground my understanding in, okay? So as far as the pictures go, all right, if we're thinking about a consistent, so the first type, the consistent linear system, that is our classic, like we've got one line, we've got another line, and they intersect only one time. All right, they intersect only one time. And so here, if I said find the solution, you would say that x comma y is the solution. All right, meaning that the place where they intersect, that's what we mean when we're saying solve this. Okay. We call this consistent for a number of reasons, but one of the ways that I kind of help myself remember that it's called consistent is like when we first learned how to graph lines and systems of equations, pretty much all our answers looked something like this, right? And so you kind of knew you were right if you drew your two lines and they crossed one time, right? So it's very consistent with what you were learning. But then every once in a while, you would graph two lines and you would end up with like one line that was kind of like this. And then you draw your other line and it would be parallel to that first line that you drew. And maybe as you drew that, you were kind of panicking. You were like, oh, I don't know if this is right. Like maybe I drew something wrong. And how come they're not crossing anywhere, right? So it was sort of inconsistent with what you had been told systems of equations should look like. But if we look at this last picture, how many solutions are there?
None?
Yeah, there are no solutions here, right? And so we would say in this case, if we did graph this, now we're sort of moving beyond that initial anxiety and saying that there are no solutions. And we're saying, okay, if this is my picture and I trust my computations, it means that there's no solutions because the lines don't cross, okay? No solutions because the lines don't cross. All right, so this linearly dependent, all right, that might be a new phrase for you, but linearly dependent means that we might have a line, right? And again, we've sort of maybe experienced this as we're working on a worksheet with like a bunch of problems, we're graphing them, and then we graph the second line and we're like, oh my gosh, it's the same line as the first line, right? How many solutions in this last picture?
Infinite.
Yeah, exactly. There's an infinite number of solutions. And why are there an infinite number of solutions?
Because the lines continue forever, and since you have to consider all the points on the line, means that it would be infinite solution.
Exactly. Remember, the solution is anytime those two lines cross. And so if you have one line and literally right on top of it, you have another line, those two lines touch at every single point. So all solutions must be on the line, okay? All right. So types of linear systems, this is going to be important because we're going to continue to build on that when we get into 3 dimensions later, okay? So that being said, let's take a look at this, all right? Solving systems of equations with graphing. I think for the sake of time, let's pick one of them and graph that one together, all right? So folks, would we like to take a look at number 1 or number 2?
2.
2, okay. So number 2, if we were to graph this, all right, so our directions here are to solve with graphing, and we were to graph these, what would we do to this first equation? So you can think of a number of strategies, but I'm wondering what your thoughts are on strategies.
Could you move pretty much the y to one side and then put it into I think it's called point slope form?
Yeah. So I think over here, if we can isolate the y, then we can get a y equals mx plus b. And then we could graph knowing what our slope is and what our y-intercept is. Exactly. So if we did that, we could get 5y equals 25, 2x plus 25. All right. And in order to get y by itself, I have to divide by 5. I'll get y equals 2/5 x plus 25. True or false?
True.
False. What did we forget to do here?
Oh, divide the 25 by 5.
Yeah, we got to divide every term by that. All right. And I make that a point because it's a mistake we've all made at some point, right? We're moving too fast through the problem and we forget. But now we have a version of the pink equation that looks something like this. And we can graph that, right? We're going to go here for the 5. True or false?
False.
Why is it false?
Because that's the y-intercept.
Yeah, exactly. 5 represents the y-intercept, but I just drew an x-intercept, right? So these are some classic mistakes that happen. So we want to go ahead and put that there. How do we find the other points on this line? What's our process?
You look at the slope, which is a rise of 2 and a run of 5. So you go up 2 and then right 5. And then to do the opposite, you go down 2 and then left 5.
Exactly. We've got our rise over run built in there, right? And so if I sort of zoom in on this, we're going to go a rise of 2 and we're going to go over 5, rise of 2 over 5. And I could do the same thing in the other direction. And then if I go ahead and graph that line, I get something like that. Yeah. All right, let's do the same thing over here. I get 5y equals 4x plus 35. I'm going to divide by 5. I get 4/5 x plus, I'm not going to make the same mistake. So 35 divided by 5, just to remind myself that I have to do the division of both terms. And I'm going to get an equation that is 4/5 x plus 7 as my green equation, right? Same thing, I'm not going to make the same mistake. So I am not going to plot the 7 over here, but I am going to plot it on the y-axis. And from here, I can count a rise of 4, a run of 5. So we'll get 1, 2, 3, 4, and 5. I think that brings us up here. 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. Go ahead and connect all those with the that's not very straight line. That's better. Okay. And this is all fine and good. We've graphed it, but we have not yet identified our solution. What is our solution?
It's the point -5, comma, what is that, 3?
Yeah, I think so. So our solution is the point -5, comma 3. Okay. And so you can take a look at example 1 on your own time. If that is something that you're like, oh, I don't really know about this graphing thing, you can practice that. You can check your answers on Desmos and you have a model example right here. Okay. One note here when using graphing, all right, I would choose this method if I had nice numbers. Okay. Meaning like there's no fractions, small numbers, right? So if I had like a y-intercept of 100, maybe I don't want to sit and draw that out, right? So smaller numbers might be a good clue that I could use graphing, or there's no fractions, that's a good clue for graphing. I like that we're thinking y equals mx plus b, and noticing that m is our rise over run, and our b is our y intercept. But either way, a good skill to know and a good skill to be able to rely on, to be able to do it accurately and efficiently will definitely help set us up for success. Okay. Let's go ahead and take a break. So it is 10:39. All right. Let's be back at 10:55 a.m. All right, so we'll take a little bit of a longer break this morning. When we come back, we're going to do something similar. We're going to take a look at one example of substitution, one example of elimination, and kind of think about this idea of when we might want to use those. What are our clues that we should use those strategies? And then we'll finish up to that section with a word problem as well. Okay, so I'll see you folks back here in about 15 minutes. And same thing here. Do we have a preference on which problem we take a look at, either example 3 or example 4? Example 4. Okay. All right. So if we take a look at example 4, all right. So if we're thinking to look at substitution, I think this one actually is very similar to what we did in our word problem in the very beginning, right? In fact, it's actually done some of the work for us already. And in particular, we might notice that everywhere we see an x, we can replace it with y plus 3. And so that means in the other equation where I see the x, I can put y plus 3. Okay. And so if I substitute that in, I would get 4 equals 3y plus 3 minus 2y. True or false?
False.
Why is that false?
Because you have to distribute the 3 to the plus 3, so it'd be 3y plus 9.
Exactly, right? We're missing a very critical set of parentheses here. So we want to just make sure we do that so that we can distribute to everything we need to distribute. And we get 4 equals 3y plus 9 minus 2y. I'm going to add the 3 to the other side, or add the 9, or subtract the 9 to the other side. So I'll get negative 5 equals, let's see, 2y taken away from 3y gives me y. Right, so we get y equals negative 5. Now, same thing here. If you stop here, you're going to be super sad about it because you didn't solve for x yet, right? And so let's think about efficiency, because nobody wants to spend more time than they want to on a problem, right? So what is the most efficient way to find x at this point?
Plug the y equals negative 5 into the x equals y plus 3.
Perfect. We're going to go back to that equation, x equals y plus 3, and we'll get x equals negative 5 plus 3, or negative 2. All All right. And typically when we write our answers for these, let's think back to what it means on a graph. What we have here is one X and one Y value. And so our solution is -2, -5, right? The solution is where the two lines, if we graph them, intersect. All right. I like that we picked number 4 because I think that's a very classic case of substitution. What would we have to do to example 3 to make it look more like example 4?
We could clear for x by sending y to the other side, subtracting, and then multiplying it times a negative in the first equation.
You could, yep, you could move the y to this side and then divide by that -1. I argue that there is a even more efficient way to do that. Yeah, we could actually just move the x, right? And then we would get y all by itself without having to do any division afterwards. So what you said first is absolutely correct, right? Mathematically, that is correct. And if we can find a more efficient way, that might actually be more helpful, okay? All right, so a couple notes on when to use substitution. I like to use substitution when X or Y is already isolated, right? Meaning that you already have an X or Y all by itself. You don't have to do any work. I would say the second time that I would say, oh, I definitely want to use substitution is if X or Y has a coefficient of +1 or -1. And the reason why I would say that is if you think to example number 3, right? If you add X to this side, you already have Y by itself. You don't need to divide by a number. But if I wanted to get X or Y by itself in the second equation, that would be like a lot more work because I'd have to add some things and then I'd have to divide and I might end up with fractions and then I got to put that into another equation. And that just seems to be more complicated, right? It's mathematically correct. There's no reason you can't do that, but it's like overkill, right? If there's a more efficient way to get there, maybe we start to look for those so that we can do less of the actual computation, okay? All right, any questions on substitution? All right, let's take a look at elimination here. Do we have a preference on which one we take a look at?
Can we look at 6?
Sure, absolutely. All right, so let's take a look at 6. What could we do? And I think this kind of goes back to what folks were doing in that launch activity, right? Sometimes we got to multiply by some things. What could we possibly do here?
You could do the x minus 2y equals 11 times that whole thing by 3.
Okay, so we multiply this times by 3. That would make the x's have the same coefficient. That would be nice. Yeah. What's another thing we could do? If we didn't want to multiply by 3, that second equation, what else could we do?
We could multiply the x minus 2y equals 11 by 5, and then multiply the 3x plus 5y by 2.
Yeah, exactly. If we do what's written in the purple, that will make the y values have the same coefficient, right? But even in just like what I'm writing out, I think we can see that the one in the purple, while it's mathematically correct, would actually take more time because I have to multiply two different equations. Whereas if I choose more cleverly, then I can make less work for myself if I just multiply by 3. Now, I'm actually going to suggest that we do this. Times by -3, okay? Here's why. I don't know about you, but I'm better at adding than I am at subtracting, in the sense that it's faster for me and I make less mistakes. So if I multiply by -3, let's see what we get. Like the first equation, or this one would become -3x plus 6y equals -33, right? If I multiply by -3, that's what I get. Now, if I stack my two equations, 3x plus 5y equals -11, and I stack that on top of the other equation, do I add these equations or do I subtract them? We add them. Right? We add them. This is where that comes into play, where I said I'm better at adding than I am at subtracting, right? If I had to subtract, what if I forget to distribute a sign, right? That could lead to some mistakes, but the way I've created the second equation, all I need to do is add the two equations. So I don't need to worry about distribution. So 3x minus 3x gives me 0. 5x plus 6x, or 5y plus 6y gives me 11y. And I get -44 on this side. So I don't have to worry about any of the like subtracting and did I distribute anything, okay? You can also times by +3 and then subtract. You'll get the same answer down here, right? So you don't have to do it this way, but if you find yourself making sign mistakes, then this could be a good strategy for you. We get y equals -4. That is part of our answer. You tell me which equation is most efficient in helping us find the value for x.
Second one.
Yeah, that second one, right? This one right here, if I grab that equation, x minus 2y equals 11, and I plug in -4 for y, I get x minus 2 times -4 equals 11, or x plus 8 equals 11, or x equals 3. And could you plug it into the first equation? Absolutely. Could you plug it into this equation? Absolutely. You have so many choices, which can be like overwhelming sometimes, but you have all of these choices. And it's okay to say, I'm going to choose the one that is the easiest for me to work with. Okay. Now, all of this to say that our solution is what? What is our solution here?
3 comma -4
Ah,
parentheses.
absolutely. How come you didn't say -4 comma 3?
Because -4 is the y value.
Yeah. And the only reason I ask that is sometimes when we're in a rush, right? The first one we found, we put that in the first spot, and the second one we found, we put it in the second spot, right? But if we take a moment to think about what our numbers mean, we found y, so that goes in the y spot, and then we found x, so that goes in the x spot. Okay. And so there's another example for you to try on your own if you feel like that is something that would be helpful for you, right? But when to use elimination? I would say this, if you see the same coefficient for a given variable in both equations. All right. Meaning, if we look at example 5, which I know we didn't do yet, we have an x and we have a negative x, right? They both have a coefficient of 1. One of them is negative, but I don't have to multiply by anything. So what I want to add to this is ideally, all right, ideally, look for coefficients that have the same number, but opposite signs. Right? If they have opposite signs, sort of like we created in example 6, we can add them together. We don't have to worry about subtracting or distributing that negative sign and maybe making a mistake there. Okay. So that is a quick review on elimination. Now, if you're feeling like what we've done today is like really, really unfamiliar for you, that happens. That's okay. There are office hours, there are tutoring sessions that you can go and get some extra support around that. Okay, so no worries if you're like, I don't really know, we're going through this a little fast. Okay, there are ways to make that better. All right, so let's finish off this section by talking about money, all right? Because I think all of these equations, like why do we need to learn how to solve them? Because they're applications, right? Because they can help us figure out when we're going to start to make money if we're starting our own business, or when we're going to have to, we'll actually be done with payments on a car or on a house, right? There's so much power behind the equations, mostly because they help you answer questions about things in your life, not because it's all just about solving equations, okay? And so let's consider this as like a pretty classic example. So we're given a cost function, all right? So we have cost is represented by C of X, which equals 0.85X plus 35,000. And the revenue function is R of X equals 1.55X, all right? And so if you think about this, our cost and then the amount that you're making, all right, how can we translate that into this idea of a break-even point?
I'm thinking it's like if you make, say, $100 and then your costs are $100, that would be 0. So
Yeah, exactly, right? The break-even point. Oh, what's happening? Okay. The break-even point is when we actually stop being in debt, right? Like maybe we had to put down a bunch of our own money to start a business, and that was really scary. But the hope is that at some point, the income will actually outweigh the cost, right? You'll actually start to make money. And so the idea of this break-even point is exactly the intersection of C of X and R of X. Okay, so when your cost equals your revenue, at that point, after that, you'll start to make money, all right? Now, how do I write intersection of two functions as an equation? That's a really important concept.
like I said, you could probably just replace the C X and then the RX with 0. Or no, I mean Y.
Okay. And then what would that tell us?
Then that would give us a system that we could then like plug the variables into it.
Okay. Let's kind of revisit this idea for a moment, right? So we talked earlier about types of linear system. So if the cost equals the revenue, which picture would show you where the cost equals the revenue?
Linearly dependent.
All right, and what makes you say that?
Because the lines would be the same. So whenever one of them, like I guess that would be the 0 at every single point. So regardless of if it was $100 or $1,000, if you subtracted those from each other, it would be 0.
So, question for you. Let's maybe write this separately. If I say that C of X minus R of X equals 0, how else can I write this equation? Okay, yeah, I could add R of X to both sides, right? So C of X equals R of X. Okay. So this is absolutely fine, right? And if you were looking to solve that, at some point you would probably add the R of X to the other side. But conceptually, what I really want us to think about is when we're looking for an intersection of two functions. This is the same as saying C of X is equal to R of X. Okay, so when you say that, oh, I'm looking for the intersection of two functions, it means find out where those two functions are equal to each other. Now, I'm making a really big deal about this because we're going to use this a lot in Math 104, but especially in Math 150 in the spring, right? So this is a really important idea that if you want to find out the intersection of two things, then you set them equal to each other, right? And so if we take our C of X and we set that equal to R of X, and then we can grab the equations that we were given earlier. So 0.85x plus 35,000 equals 1.55x. All right. Now, if I had given you this equation, yeah, it has decimals, but I feel like we would be able to solve that pretty confidently, right? And so part of this is really about creating the equation. Not just can you solve it, but how do you get to the equation? All right. And I know that's scary for a lot of people, but I want us to kind of embrace that space and like in our heads be like, I can do this. I can learn how to do this, even if it's been confusing to me all these years. It is something that I can master. All right. So if we are going to solve this, how do we solve this?
Well, we can solve for x, right? So We can put like terms together. So you can subtract 1.55 by 0.85x.
Okay, and so if we move that 0.85 over, we do a little computation. I think we get 0.7x. And then to get x all by itself, we just got to divide by that 0.7. And I think we end up with that. Okay. And so this is a really stripped down word problem, but I think if we think about it in the context of like, you know, selling a product, right? Let's say that you're selling some sort of product. If you sell 50,000 units of whatever you're selling, then you will be at your break even point. Okay, then you will be at your break even point. Now, I wrote this earlier as C of x minus R of x equals 0. I could have also written it as R of x minus C of x, meaning the amount I make minus the cost, right? So whatever I make and I take away the cost, that is what tells you how much money you make, your profit. And so to write this profit function, even though that might be like, oh, I have to write a function and that seems like a scary process, all we're doing is thinking about what it means to be a profit, right? That we're thinking revenue minus cost. We're plugging in the equations that they gave us. And then we are simplifying that to get our profit. True or false?
False.
Okay, why is that false? What are we missing?
You didn't distribute the minus sign to the 35,000.
Yeah, right. This minus sign, it's got to go to that plus sign. And so I can remedy that by making sure I distribute and getting 0.7x minus 35,000. Okay. And I feel like this is actually another way to look at that break even point, right? You can say, when is the profit equal to 0? That would be another way to find that break even point. When is P of x equal to 0? Or when is R of x equal to C of x? All right. I think logistically, for like if you are literally doing a problem where you're trying to figure out how much, I think the profit is sort of a nice way to look at it. But it was as we move into the other classes that we're going to be doing together, knowing that like an intersection point means when are two things equal to each other is actually going to be important for us in a different context. Okay. All right. So that finishes up 9.1. So I'm going to stop the recording here.